Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International GCSE Chemistry Paper 1C for November 2023. Let's begin with the first question. In question 1, a substance can exist in 3 states of matter, solid, liquid or gas. When a liquid evaporates at room temperature, it changes into a gas. Complete the diagram to show the arrangement of another 4 particles in a gas. So remember, particles in a gas state are arranged far away from each other. So any 4 particles placed in a disorderly way and far away from each other would work, like how I represented them here. In part B, explain why heating a liquid causes it to evaporate more quickly. When a liquid is heated, the kinetic energy is going to increase, meaning the particles will possess more kinetic energy and they will move more quickly. So more particles will have the energy that is required to escape from the solution due to the ability to break the intermolecular forces of attraction that are holding the particles together. So in this case, more particles will move to the surface of the liquid in order for the intermolecular forces to be completely broken, for them to evaporate away from the liquid into the gaseous phase. In part C, when the temperature decreases, water in the gas state changes to a liquid. Give the name of this change of state. This is going to be condensation. And next they say write an equation including state symbols to show the change of state of water from a gas to a liquid. This is going to be water gas becoming water liquid, and that is how you're supposed to represent that. And next they say describe the arrangement and movement of particles in a solid. In a solid state, the particles are going to be arranged in a regular manner and they're going to be close to each other. They will only vibrate, but they cannot move, and they're going to be vibrating around fixed positions. So this brings us to the end of question 1. Let's continue to question 2. In question 2, table 1 shows some relative masses and charges of subatomic particles. Complete table 1 by giving the missing information. So here they've given us the relative masses and we're looking for the relative charge. Each electron has a charge of -1. A proton has a relative mass of 1 and a charge of +1 because protons are positively charged. Neutrons have no charge, but they have relative mass 1, so that should be the answer to that part. And next they say table 2 gives the number of protons, neutrons, and electrons in atoms and ions of some elements. The letters are not the symbols of the elements. So the first question says, what is the atomic number of P in the table? The atomic number should be the number of protons. So because P has 3 protons, it means its atomic number is going to be 3, so B is going to be our answer. Next they say what is the mass number of U in table 2. We can go back to table 2. Here U has the number of protons 8, the number of neutrons 8. The mass number should be the number of protons plus the number of neutrons, and that gives us 16. So the answer should be B. And next they say give the letter in table 2 that represents an element in group 5 of the periodic table. We can look at element S. Because it has 7 protons and 7 electrons and is in elemental state, so nothing has been lost. So it will have 2 electrons inside and 5 electrons in the outer shell, so it's going to be S. That is the group 5 element. In part C, Q and R represent isotopes of the same element. Explain in terms of subatomic particles why Q and R are isotopes. Isotopes are atoms of the same element that have the same number of protons but have different numbers of neutrons. And next I say a sample containing the isotopes Q and R has the percentage composition by mass, which is 20.6% for Q and 79.4% for R. They want you to calculate the relative atomic mass of the sample of the element and give your answer to 1 decimal place. If we go back to the table in order to calculate the atomic masses, we are looking at Q and R. Q is going to have 10 atomic mass 10, and then R is going to have atomic mass 11. So coming down here, we have 10 and 11. So calculating the relative atomic mass is going to be 20.6 divided by 100 times 10 plus 79.4 divided by 100 times 11. And combining both, I got 10.8, rounding up to 3 significant figures like they gave us here. So my answer was 10.8. So this brings us to the end of question 2. Let's continue to question 3. In question 3, crude oil is an important source of organic compounds. The diagram shows how crude oil can be separated into useful mixtures of hydrocarbons. So from this diagram, we see crude oil comes in, it's going to be heated, and then evaporation is going to occur, and the different fractions are going to be collected. They say give the name of this method of separation. This method is called fractional distillation. And next they say state what happens to the crude oil when it is in X. Here it's going to be heated to evaporation, so it's going to be vaporized. And next they say give the letter of the mixture that is most likely to contain a hydrocarbon with 6 carbon atoms. Between carbon 1 to 4 it's going to be in F, so we expect something that is 6 carbons to be in this fraction, so the answer should be E. And next they say give the name of mixture D. D is going to be the kerosene mixture or kerosene fraction. And they say give a use for mixture B. Mixture B can be used as fuel in ships. In part B, explain in terms of intermolecular forces why a hydrocarbon in mixture B has a higher boiling point than a hydrocarbon in mixture D. Now, because we are looking at hydrocarbons, having a higher boiling point is because one forms more intermolecular forces of attraction in comparison to the other. B having a higher boiling point means it has a longer carbon chain and therefore forms greater intermolecular forces. So I say the length of the hydrocarbon in B is greater than the length of the hydrocarbon in D. So stronger intermolecular forces form between molecules in B than in D. Therefore, more energy is needed to overcome the stronger forces of attraction. And in part C, catalytic cracking can be used to break down long-chain hydrocarbons to produce shorter-chain alkanes and alkenes. Give the name of a catalyst used in catalytic cracking. We can use silica or we can use alumina. Next, they say complete the equation to show 2 different alkenes that could be produced in this cracking reaction. This cracking reaction has already produced 1 alkane, so the rest are going to be alkenes. And since this is 8 carbons, it means we have 7 carbons to account for. So meaning that 2 alkenes could be a carbon 3 and a carbon 4, or a carbon 2 and a carbon 5. Both alkenes with a general formula carbon N, hydrogen 2N. So if the carbons are N, the hydrogens are going to be 2N, meaning carbon 4 hydrogen is going to be 8 and carbon 5 hydrogens are going to be 10. So either you write these 2 or you write the 2 below. And next they say give one important use for short chain alkenes. These can be used in polymerization reactions. So this brings us to the end of question 3. Let's continue to question 4. In question 4, this question is about gases. The table gives information about 5 gases. So we can see all the gases in the table. And they've calculated their specific molecular masses. Then they say use information from the table to answer these questions. Each gas may be used once, more than once, or not at all. They say give the name of the gas that is about 79% of the atmosphere by volume. This gas is nitrogen. And next they say give the name of the gas that is a compound. This is a compound here because it's made up of atoms or more than 2 different elements, while the others are all made up of single elements, so it should be carbon dioxide. Next they say give the name of the least reactive gas. That is going to be argon. And then they say give the name of the gas that is not normally found in the atmosphere. Among them, this is going to be hydrogen. And next they say give the name of the gas that affects global warming. That is going to be carbon dioxide. And to calculate the MR of carbon dioxide, it's going to be CO2, so 1 carbon, each carbon is 12, plus 2 oxygens, each oxygen is 16, giving us 44 in total, and that's the answer. So from the table, you see I put 44 to represent the MR of carbon dioxide gas. And then they say give a reason why it is not possible to give information for air in the table. This is because air is a mixture of different gases, so we cannot give its composition. In part B, when copper 2 carbonate is heated, the products are copper 2 oxide and carbon dioxide. Give the name for this type of reaction. This is a thermodecomposition reaction because a carbonate is converted into a metal oxide as well as carbon dioxide. So it should be thermodecomposition. And next they say give the color change that occurs during this reaction. The copper 2 carbonate is going to be green, while the copper 2 oxide is going to be black. And then give a chemical equation for this reaction. This is going to be copper carbonate decomposing to give us copper oxide plus CO2. And this should be the equation you write. So this brings us to the end of question 4. Let's continue to question 5. In question 5, this question is about alkanes and alkenes. The alkane, carbon 4 hydrogen 10, exists as 2 isomers. State what is meant by the term isomers. Isomers are compounds that have the same molecular formula, but their structure formulae are different. And next, draw the displayed formulae of the 2 isomers of this one here. This is an alkane, so it's either a straight chain alkanes with 4 carbons arranged in a line or in a chain, and then the hydrogens filling out. Remember, they say displayed, so this is the displayed formula. Or it could be that 1 carbon branches off from the end and is positioned on the mid carbon here to create a 2-methyl. So this is going to be the other structure. In part B, ethane, which is carbon 2 hydrogen 6, can react with bromine. State the conditions needed for ethane to react with bromine. Because ethane is an alkane, it only reacts with bromine when ultraviolet light is present, so the condition should be with UV light. And next they say complete the equation for this reaction. This is a substitution reaction, so the Br will come and substitute 1 hydrogen, and then the hydrogen will bind with the remaining Br. So we will form a carbon 2 hydrogen 5 Br plus HBr. And here the name, this is going to be a substitution reaction. In part C, explain why ethane is described as a saturated compound. It is saturated because it contains only carbon-carbon single bonds, so no other atoms can be added to it. In part D, state what you would observe when ethane and ethene are added separately to 2 samples of bromine water. Ethane is an alkane and is not expected to give a positive test with bromine water, while ethene should give a positive test. And this is because bromine water is used to test for presence of a carbon-carbon double bond. So with ethane, there is no observable change. The bromine water is going to remain orange, while with ethene, the bromine water is going to change color from orange to colorless. And in part E, explain why straight chain alkenes always have the same empirical formula, but straight chain alkanes have different empirical formulae. Refer to the molecular formulae of alkanes carbon 2 hydrogen 6 and carbon 4 hydrogen 10 in your answer. So of course with alkenes, because the number of hydrogens is going to be double the number of carbons, the empirical formula is always going to be CH2, but that of alkanes is going to be different because of the general formula. So here I said straight chain alkenes have twice the number of hydrogens as the carbons, so their empirical formula is always CH2. However, for alkanes, the general formula is carbon n hydrogen 2n plus 2. The 2n plus 2 can be divided by 2 to give a whole number ratio. So when we use carbon 2 hydrogen 6, we can see the empirical formula is going to be CH3. Well, for carbon 4 hydrogen 10, the empirical formula is going to be carbon 2 hydrogen 5, and these are going to be different because of the way the general formula for alkanes is. In part F, an organic compound has this percentage composition by mass. Carbon is 19.2, hydrogen is 4.0, oxygen is 12.8, and bromine is 64.0. They want us to calculate the empirical formula of this compound. So we begin by writing the carbon, hydrogen, oxygen, and Br, and then the percentages below them. Then we calculate the number of moles by dividing through with the atomic mass. For carbon it's 12, for hydrogen is 1, for oxygen 16, and for bromine it's 80 from the periodic table. And when I divided, I got these as the corresponding number of moles. So to get the mole ratio, I divided this by the smallest number of moles, that by that, that by that, and that by that. And I got a ratio of 2 to 5 to 1 to 1, which is carbon 2, hydrogen 5, oxygen, Br. That is going to be the empirical formula of this organic compound. So this brings us to the end of question 5. Let's continue to question 6. In question 6, a student uses this apparatus to investigate the decomposition of hydrogen peroxide solution. So here we can see the setup. There is manganese for oxide, which is the catalyst, hydrogen peroxide, and then oxygen, which is the product. They say this is the equation for the reaction. Hydrogen peroxide is decomposing to give us water and oxygen. They say give the test for oxygen. Oxygen relights a glowing splint. And next is a complete the dot and cross diagram for a molecule of hydrogen peroxide. Show outer electrons only. Hydrogen is going to be drawn as a smaller atom in comparison to the oxygens. But because hydrogen has one electron in the outer shell, that electron is going to be used in formation of the covalent bond with oxygen. And the other side is going to be the same. Then for oxygens, they only have 6 electrons in the outer shell. So each is going to have 1, 2, 3, 4. And then a single one is going to be shared in each covalent bond. The same thing here, one shared here, one shared there, and then the 4 on the other side. So this is going to be the dot and cross diagram showing only the outer shell electrons. In part C, the student measures the volume of oxygen collected at regular intervals until the reaction stops. The table shows the students' results. They say plot the students' results on the grid. I plotted these, you can see, all the way until there. And the next part, they wanted us to draw the line of best fit. I tried, and again, you can see this is a little bit shaky because I was drawing on the iPad, but you try to make it into a smooth curve in order to obtain better results. So just plot the points basically. The horizontal axis has time and the vertical axis has volume. We can see there is a point at 0, 0, there is a point at 20, 24, and then we have 40, 44, we have 60, 62, we have 80, 78, and then here we have 188, we have 120, 94, 140, 94, and 160, 94. In part D, explain in terms of particle collision theory how decreasing the concentration affects the rate of reaction. If the concentration of reactants is decreased within the same volume, it means the number of moles are going to be decreased. There are fewer reactant particles, and so there will be fewer collisions, meaning the rate of reaction is going to be slowed down. So I said decreasing the concentration within a fixed volume decreases the number of reacting particles, so fewer collisions occur per time, and the rate of reaction is going to decrease. In the next part, the student repeats the experiment using the same volume of hydrogen peroxide solution, but with half the original concentration. All other conditions are kept the same. On the grid, draw the curve you would expect a student to obtain. Because they've used half the concentration or half the original concentration in the same volume, it means the number of reacting particles are going to be half, and therefore the rate is going to decrease. Remember, the rate has to be lower, so the curve has to be inward in comparison to the other, and then it has to curve in at halfway this volume here, because this is volume of oxygen. If the concentration is half, it means the volume of oxygen collected at the end is going to be half the total volume collected in the other experiment. So it's going to be about 47 centimeters cubed of oxygen collected. And in part E, in this reaction, the manganese oxide acts as a catalyst. Explain how catalysts work. Catalysts work by providing a new pathway with lower activation energy, so more particles will have energy that is required for the reaction to proceed. So this brings us to the end of question 6. Let's continue to question 7. In question 7, a technician needs to identify the solution in an unlabeled bottle. The technician knows that the solution contains one of these compounds. So here we have 2 cations and 2 anions. The cations, which are ion 2 and ion 3, can be identified using solubility in sodium hydroxide. We'll see the colors of the precipitates formed, and then we can make a conclusion. And then the chlorides will add nitric acid, followed by silver nitrate, and then look at the precipitates formed. These are going to be silver halides. For the bromide, they're going to be cream, and for the chloride, they're going to be white. So here they say, describe how the technician can use chemical tests to identify the compounds. I say to identify the cations, add sodium hydroxide solution. If a green precipitate forms, it is ion 2 plus. If a brown precipitate forms, then it's going to be ion 3 plus. And to identify the anions, add nitric acid followed by silver nitrate and observe the color of the precipitates formed. If the precipitate is white, then the anion is going to be chloride. If the precipitate is cream, the anion is going to be bromide. In part B, when chlorine gas is passed over heated iron powder and 3 chloride forms, this is the equation for the reaction. We can see the equation. And they say 0.06 mole of chlorine gas is passed over 2.8 grams of iron powder. Show by calculation that iron powder is in excess. To answer this question, we're going to calculate the number of moles of iron using the mass provided, and then we'll compare the actual reaction mole ratio as well as the mole ratio from the equation and see if they are the same or not. So for the moles of iron, they're going to be the mass of iron given here divided by the atomic mass of iron, and I got that. So these moles of iron will require 3/2 times 0.05 moles of chlorine, which should be that. However, we can see they've given us only 0.06 moles, which is less than the 0.075 required. So it means we have less chlorine, and therefore iron is going to be in excess. And in part C, when iron 3 chloride dissolves in water, an acidic solution forms. Give the color of litmus in this solution. Litmus paper turns red in acidic solution, so the answer is going to be red. And next they say give the formula of the ion that causes the solution to be acidic. This is going to be the H+, which is found in all acids. So this brings us to the end of question 7. Let's continue to question 8. In question 8, diamond and graphite are made of carbon atoms joined together by covalent bonds. The diagram shows their structure. So here we have diamond and here we have graphite. They say state in terms of electrostatic attractions what is meant by a covalent bond. This is the electrostatic force of attraction between two nuclei and a pair of shared electrons between the two atoms. And in part B, explain why diamond has a high melting point. If I take you back to the structure of diamond, we can see each carbon atom is connected to 4 other carbon atoms, creating a structure which has so many covalent bonds. So those covalent bonds are harder to break and they will require a lot of energy for them to be broken. So I say diamond is a giant structure with multiple covalent bonds, or I could say with multiple strong covalent bonds. And these require large amounts of energy to be broken, so their melting point is going to be higher. And in part C, explain why graphite is a good conductor of electricity. If I look at graphite, each carbon atom is bonded to 3 other carbons. If I look at this carbon, we can see there is 1, 2, 3. It's bonded to only 3 other carbon atoms, leaving 1 delocalized electron per carbon. And so when a potential difference is applied, electrons are going to flow through the structure because of the delocalized electrons. So I said graphite contains a delocalized electron per carbon, and when a potential difference is applied, the electrons move to conduct electricity. In part D, carbon-60 fullerene is a molecule made of 60 carbon atoms. The diagram shows the structure of carbon-60 fullerene, which is this one here. They say 1 mole of atoms contains 6.0 times 10 power 23 atoms. Determine the number of atoms in 1 mole of carbon-60 fullerene. So they want us to give the answer in standard form. To find the number of atoms, it's going to be the number of moles times the 60 times this number here they've given us. So since it's 1 mole, this is going to be 1 times the 60 atoms times the 6.0 times 10 power 23, and this gave me 3.6 times 10 power 25 atoms, so that should be my answer. So this brings us to the end of question 8. Let's continue to question 9. In question 9, a scientist uses this apparatus in an experiment to reduce a metal oxide to a metal. So here we can see hydrogen is passed over a metal oxide. So that means a metal oxide is reacting with hydrogen, and this is going to give us a metal and water. So the excess hydrogen is going to be burnt off to prevent it maybe from filling the lab. It could be dangerous because hydrogen can catch fire or it can explode. So before heating, the mass of the empty tube and the mass of the tube and the metal oxide are recorded. After heating, the tube is allowed to cool and the mass of the tube and its contents is recorded again. Part SA states why the reaction of the metal oxide to form a metal is described as a reduction reaction. Oxygen is lost by the metal oxide. And next they state why it is important to relight the hydrogen at the end of the tube if the flame goes out. I've already talked about this. Hydrogen is flammable. Hydrogen can explode. So this is a precaution in order to prevent accidents because hydrogen can catch fire explosions can occur, and this could endanger people. And next they say explain why it is important to continue passing hydrogen into the tube and burning the hydrogen at the end of the tube until contents have cooled. This is because if they stop passing hydrogen over the metal, then oxygen is going to come into the tube, and then the metal is going to be reoxidized at those high temperatures, so you produce the metal oxide again. Next they say describe what should be done next to ensure that all the metal oxide has been converted to the metal. Here all we need to do is to heat along with the contents, then you reweigh. Of course you have to cool, reweigh, and then repeat the cycle until the mass is constant. So basically we heat to constant mass. In part B, in this experiment, a mass of 4.14 grams of metal is formed from 4.46 grams of metal oxide. Calculate the amount in mole of oxygen atoms in the sample of the metal oxide. Now to write this equation again, placing the respective masses, this is going to be the metal oxide and that is going to be the metal. The mass of oxygen present, and again I'm using oxygen atom, the mass of oxygen atoms present is going to be the mass of the metal oxide minus the mass of the metal. So oxygen atoms is going to be 0.32 grams. So the moles of oxygen atoms present is going to be 0.32 divided by 16. Again, I'm using atomic mass, not molecular mass. And this gave me 0.02 mole, which are the amount of oxygen atoms. And next they say the formula of the metal oxide is MO, where M represents the symbol of the metal. Deduce the amount in mole of M in the sample of the metal oxide. In 1 mole of this, we have 1 mole of oxygen. So the number of moles of the metal are also going to be 0.02. And next they say calculate the relative atomic mass of M. The relative atomic mass is going to equal to mass divided by the number of moles. Remember the mass of the metal is 4.14 grams. So 4.14 divided by 0.02 gave us 207. That is the relative atomic mass. And then they say use the periodic table to identify the metal. This is going to be lead. Its atomic mass is 207. So this brings us to the end of question 9. Let's continue to question 10. In question 10, this method is used in an experiment to produce hydrated zinc nitrate crystals. Pour 50 centimeters cubed of dilute nitric acid into a beaker. Add a spatula of zinc powder to the acid, then add more zinc until it is in excess. Filter the mixture and obtain crystals of zinc nitrate from the filtrate. So they say state why the mixture is filtered. Looking at this reaction I wrote here, zinc is going to be a solid and it's going to be in excess. So once the reaction is completed and all the acid has reacted, the excess zinc is going to be left. So we filter so that we get zinc nitrate. And in part B, they say describe how a pure dry sample of hydrated zinc nitrate crystals could be obtained from the filtrate. So here we can use an evaporating basin, pour the sample of zinc nitrate, evaporate off some water, and then you will heat until crystallization point. The crystallization point is when you put a glass rod and take it out and see some particles begin to form as the glass rod cools. So once that point is reached, you let the saturated solution to cool down. Crystals are going to form, and then you filter to obtain the crystals. Then these crystals can be dried between filter papers or in a warm oven. In part C, this equation represents the formation of hydrated zinc nitrate in the experiment. We can see the equation. They say in another experiment, 9.75 grams of zinc is completely reacted with nitric acid. Show that the maximum possible mass of hydrated zinc nitrate crystals that could be formed is approximately 45 grams. Because they've said could, it means we are looking at the theoretical yield. Based on the stoichiometric equation, if all conditions were fulfilled, with 100% yield, this is what we're going to get. The mass is going to be closer to 45. So here we need to begin with zinc. Moles of zinc are going to be that mass divided by the atomic mass of zinc, which is 65, giving us 0.15 moles. And then the mole ratio is 1:1, so the number of moles of the zinc nitrate or the hydrated zinc nitrate is going to be also 0.15 mole. So the mass of the hydrated zinc nitrate is going to be number of moles times the molar mass. giving us 0.15 times 297, and I got 44.55 grams. This is approximately 45 grams, and so that should be correct. And lastly, they say the actual yield of hydrated zinc nitrate is 36.4 grams. Calculate the percentage yield of zinc nitrate crystals. The percentage yield should equal to actual yield divided by theoretical yield times 100. So this is the actual yield. So I have 36.4 divided by the 44.55 times 100, and I got 81.7% as my percentage yield. So this brings us to the end of question 10, as well as to the end of this whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.